Welcome to today's tutorial. So today we're looking at thermal expansion in physics. My name is Harmtedy. Okay, so let me start first by introducing what thermal expansion is. So we know to say every substance when exposed to temperature, they can either expand or contract depending with the temperature. Yeah. Okay, so let us look at the types of expansions. We have what we call linear expansion, area expansion. There's also what is known as the volume expansion. So let's start first by discussing linear. So when an object, for instance, when you have a rod, the iron rod, when you expose this to heat, it has the length L0, which is the initial length. When you expose this to heat, you expect it to expand. It's going to increase in the length, so this will be called the final length. So to find the change in the length, you say that the change in length is just given by the final minus the initial length. So the change in length is just this part here. This is the change in length. So now to find this distance, you just say the final length, which is L minus the L initial. You get this distance. Okay, so this change in length can also be found by using this formula, which is alpha L0, the change in T. Yeah, alpha L0, the change in T. So this alpha is just a coefficient of linear expansion, and then L0, we know that it's just the initial length, and then the change in L is just the difference in temperature. Yeah, so you know that when the iron rod was like this, you got the temperature, maybe for instance this was 20 degrees. Yes, and then after increasing this temperature maybe to maybe 130 degrees, if you increase this temperature to 130 degrees, you discovered that the rod was like this. It expanded to this distance, hence you put your change in length there. And this T is the absolute temperature. So whenever you're using this T, make sure that you convert it to Kelvin. But we know to say the difference in the temperature in degrees Celsius is just the same as the difference in temperature in kelvins. So when you're using this formula, there's no need of converting. Okay, so let's quickly move on. So having been told how to use this formula, let us now look at the area expansion. So for the linear expansion, it was just the length which was expanding, but for the area expansion, we expect to have a particular area to expand. For instance, if you have a disk like this, so this disk when exposed to heat is going to expand, so meaning the area, this area is going to expand or decrease when exposed to the temperature. So for this one, for this one, the formula is almost the same. Yeah, it's almost the same. So you just say the change in area is equal to the original area minus the initial area. Sorry, this is A minus the initial area. And then in terms of this formula, it's also just the same. It's going to be, but in this case we're not going to use alpha, we use gamma. So area is equal to gamma times the initial length and then times the change in temperature. So this gamma will not be given. The alpha, the linear, the coefficient of linear expansion is always given, but gamma will never be given in an exam. So how do you find gamma? So you find gamma by just using this formula, this simple formula, which is y is equal to 2 alpha. So this gamma is not exactly equal to this, hence we don't use the equal sign. Sorry for writing that. We use the approximate equal sign approximation. We just approximate to say this gamma is equal to, or is approximately equal to 2 alpha. Yeah, so gamma is approximately equal to alpha. So let us now yeah, the temperature is just the same way talked about these temperatures, the same way you apply it here, that's the same way you apply it there. Yeah, so after looking at the area expansion, we can also look at the volume expansion. So imagine you have something, you have a beaker like this, then you put a liquid inside there, a fluid. Yeah, you have a fluid inside the beaker. We know that water has unusual characteristics when exposed to temperature. So I'm not going to use water, let me just use a general term, which is a fluid. So if you put a fluid there, you expose this to a certain temperature, you expect it to either contract or decrease in the volume, or expand, or increase in the volume. So the same way we did this, that's the same way you do with the volume. So we know that the change in volume will just be equal to V minus V naught, which is the original volume, which is the final volume minus the initial volume. So this can also be written as the change in volume is equal to, in this case we're going to use beta, and then beta times V naught, which is the initial volume, and then times the change in temperature. So the same way I explained on the change in temperature on the first one, that's the same way you do it here. Yeah, so except that you have to know that this beta is just equal to 3 alpha. Of course, this is not also equal, we use equivalent. So this is also not equivalent, we use approximate. So we say this beta is approximately equal to 3 alpha. Okay, so this is all about linear area and volume expansion. Let's now take a look at some questions. How do they ask these questions? Yeah, so let's take a look at this question, which was the first question in the exercise that I gave in my tuition group. So the question reads, an ordinary glass is filled to the brim with 450 ml of water at 100 degrees Celsius. If the temperature of the glass and water is decreased to 20 degrees, how much water could be added to the glass? Sorry. Okay, so let's discuss this quickly. Okay, so what we need to understand here is that they are saying the ordinary glass is filled to the brim with 450 ml of water at 100 degrees Celsius. If temperature of glass and water is decreased to 20, how much water could be added? So if, for instance, we have a glass like this, we have a glass of water, and then this glass of water is filled to the brim. Yeah, it's filled to the brim. There is water in this glass, and then they are saying this glass was initially at 100 degrees when the volume was 450 ml. So the volume was 450 ml, the temperature was 100 degrees Celsius. Now what happens if they decrease the temperature? So if they decrease the temperature, we know that according to the anomalous behavior of water, we know that when water is increased from 4 degrees going up, it increases in volume, and when it's decreased from, if the temperature is decreased from 4 degrees to 0, it increases in volume. Something like this. Let me just write it quickly here. Something like this. 1, 2, 3, 4. So I'm going to discuss this tonight. You have something like this, then it goes up. So any temperature above 4 degrees Celsius, increases the volume of water. Okay, so let's quickly let me just erase this. Okay, so now this is what they are talking about, and then they are asking to say what happens if you decrease the temperature to 20 degrees. So you expect the water level to also go down. You expect the water level to also go down. So now if the water goes down, how much water could be added to the glass for this glass to be full again? How much water can we add there? So we can now derive a formula from what I've just discussed here to say the water that can be added, or the volume of water that can be added, the volume of water that can be added is simply just equal to the difference in the V finals. So the V final of the glass, the volume of the glass, the final volume of the glass, so say VF of the glass of water, or let me call it container, minus the final volume of water. So this is what we're going to use to find the water that can be added to the glass for it to be full. Okay, so the V that we're going to, we know to say the V final here. So let me say V, the volume of water that we're going to add is equal to, so we know to say V final, so let me say, but VF we know to say is just given by V initial, V naught, this is V naught plus the change in V, because we know to say V final minus V initial is equal to the change in V. So what I've just done is that I've just taken V initial to the other side of the equal sign. So we can say V naught plus the change in V of the container minus V naught plus the change in V of water. So from there we can now say so from there we can now say V naught, and this V naught of water and the V naught of the container, we know that these are going to be the same. How do I know that? Because I was told to say initially the water was filled to the brim, meaning the volume of water was equal to the volume of the container. So this V naught and that V naught will go. So just remain with, so the volume of water added will just be equal to the change in volume of the container minus the change in volume of water. So the volume of water added is equal to the change in volume of the container. We know to say the change in volume of a container is given by we know to say the change in volume of any given substance is given by beta. It's given by beta V naught change in temperature. So we're going to have the beta V naught change in temperature of a container minus beta V naught change in temperature of water. So from there we can now say the volume of water that has been added is just equal to so the volume of water that has been added is just equal to we know to say V naught and V naught are the same, and the change in temperature and the change in temperature, they are the same. So we can just simply factorize. We say B of the container, the beta of the container, minus the beta of water, and then this times V naught times the change in temperature. Yeah, so V naught and the change in temperature are just the same. So from there we can now just plug in the values. So what have we been given according to the question? So the B of the container, you get it from the table. If you're writing an exam, they'll give you this at the front page, I mean on the second page of the question paper. So this you can get them from the table. So container, and then yeah, I'm sure you're asking yourselves which table. Most physics, pure physics books, they have this. They only contain alpha. So meaning to find B, you just say 3 times alpha. We know to say 3 times alpha is just equivalent to beta. That is what we're just from discussing. So B minus B of water, and then the volume has been given to be 450 mils, and then the change in temperature will be, the final change in temperature is what? The final temperature was 20. So this will be 20 degrees minus 100 degrees. That was the initial temperature. So 20 degrees minus 100 degrees, so we expect our volume of water added to be equal to container minus for water, and then expect this to be 450 mils there, multiplied by negative 80. Yeah, so once you calculate this, after doing all the calculations, getting the tables from the, getting the values from the table, and then I provided the values of this in my lecture slides. Yeah, in my lecture slides the table is there where you can get these values. So after finding all this, the answer you're supposed to get is 6.59 mils. So this is the answer that you're supposed to get. Alright, so let's quickly move on to the next question. Okay. Alright, so question 2 reads, so question 2 is, to what temperature would you have to heat a brass rod for it to be 15% longer than it is at 25 degrees? So for this one, longer, just from the word longer, you can tell to say what they want is the length. Actually, the question even reads to say to what temperature. So for this, just by reading at this word longer, meaning this 1.5 is simply the ratio of the length. Yeah, and then they want us to find the temperature, but we know to say the formula is given by the change in length is equal to the coefficient of linear expansion times the initial length times the change in temperature. So they want us to find T final. Yeah, they want us to find the final temperature, because we've been given to say the initial temperature was 25. Now they want us to find the temperature that we increase it to what length, to what temperature would you have to heat the brass rod for it to be 1.5 longer. Yeah, so they want us to find the final temperature such that if we heat this rod, if we heat this rod to that temperature, the length will be 1.5 longer than the initial length. Yeah, so the change in length is given by that. So the change in temperature is just given by we make delta T the subject, so we're going to have the change in length over alpha L naught, alpha times the change times the initial length. So from there, the other thing that we need to know is that this 15% is simply just the ratio of the change in length and yeah, the ratio of the change in length and the initial length. Okay, so the delta t this side, we know that this is just given by t final minus t initial. So this is equal to we know to say delta t over L naught is simply just equal to, so if this is 1.5%, so if this is 1.5% longer, means that we're going to have something like 1.5 this side over yeah, over the original, which is just 1, in short, which is just 1. So for us to get the proper, what's this, 1.5%, for us to get the proper fraction here, we can just multiply all this. Sorry, we divide this by 100. We divide this by 100 because this is a percentage. This is 1.5%, so we're going to have 1.5 divided by 100. Yeah, so this will give us something like 0.015. Okay, so this is what we have as our delta L over L. So we put it there. We can put our delta. Okay, before we even do that, let me just write this again. Let me just rewrite this. So this is what we have. Then from there, our delta, we can plug in our the values, or if we want, we can even make t the subject first. This will be t naught, then plus delta L over alpha L naught. So from there, our t naught becomes, our t naught has been given to be 25 degrees, and then that 25 degrees we add it to the change in length over L. That one we found it to be 0.015. Then we divide everything by the alpha. So the alpha of brass, when you check the table, is somewhere around 19. This is 19 times 10 to the power negative 6, and then the units are just per degrees Celsius. So when you divide this, you get your answer to be something like 814.5 degrees. So degrees Celsius. So this is the temperature that they wanted you to find. Let's move on to the next question. Alright, so this is question 3, which reads an air bubble at the bottom of the lake 41 meters deep has a volume of 1 cubic centimeters, or 1 cubic centimeters, and then here there was supposed to be a full stop. There's supposed to be a full stop there. And if the temperature at the bottom is 5.5 degrees Celsius and at the top is 18.5 degrees, what is the radius of the bubble just before it reaches the surface? If the air bubble at the bottom of the lake 41 meters deep has a volume of 1, if the temperature at the bottom is this and then at the top is that, what is the radius of the bubble just before it reaches the surface? So this one I wanted you to study further before we start the next topic, which is the gas law. Yeah, the ideal gas law. Yeah, so we use the ideal gas law to solve this equation. We know to say PV is equal to nRT. I'm sure you did this in secondary. So we know to say the PV over T is equal to nR. So nR is just a constant. This one is just a constant. Yeah, so This one gives you the constant. So if we say the constant according to mathematics, if we put a constant this side, it means that we can write it as P1 V1 over P2 V2. Oh, sorry, not like this. You can write it as P1 over, P1 and then T1 this side. This can also be written as P2 V2 over T2. And then from there, so from there we can now say, so we have a lake. So the good part with physics, you can be imagining what you are reading. You have a lake, and then it is 41 meters deep, and then so this is a lake, and then there's a bubble at the bottom. So it starts going up. So as it is going up, it will either reduce or increase in size depending with the temperatures. So they are asking us to find the radius of this bubble before it reaches the surface. So now we can say our P1, if this is 1, if I'm going to call the deep of this lake to be 1 and then the surface to be 2, we're going to say we're going to make V2 as the subject, or maybe let me do it the other way around so that it becomes easier for us to understand. So I put this as 1 and then I put this as 2. So I'm going to make 1 the subject because they wanted us to find, they want us to find the value of the radius before it reaches 0.1. So let us make V1 the subject. So if we make V1 the subject, this will be equal to P2 V2 over T1. Of course, on top there, if we cross multiply, we need also to have T1 there, over T2. Then we need also to have T1 there, and then P1 down. So we can write it properly as P2 over P1, and then T1 on top over T2. Let me just draw one division line. Let me write them properly. So I'll draw one division line there. So I'm going to say P2 over P1 times T1 over T2, and then multiply everything by V2. So V2 is just the volume at the at the bottom of this lake. And then the other thing that you need to understand here is the pressure at point 2. The pressure at point 2. Pressure at point 2 is given by. So the pressure at this point is given by. Pressure at point 2 is given by the atmospheric pressure. We know to say there is a pressure from the atmosphere there. So this is the atmospheric pressure, which is P atm plus rho GH. So that is the pressure there. And then pressure at point 1 is just equivalent to the atmospheric pressure, which is P atm. So the pressure at point 1 is just the atmospheric pressure. And then at point 2 we have two pressures. We have the atmospheric pressure and the pressure due to the water. So we can rewrite this as V1 is equal to, so V1 is equal to P2 is simply just P atmospheric pressure plus rho GH, and then over the atmospheric pressure, which is the pressure at point 1, and then everything times the temperatures have been given. So make sure that when you're writing these temperatures, you convert them to Kelvin. Convert them to Kelvin. You have T1 over T2, then multiply everything by the volume. You multiply everything by the volume, which has been given to be 1. So the volume has been given to be 1 cubic centimeters. So you also write it there, which is your V2. The volume of a bubble at this point has been given at the bottom, so you write it there. So after doing all your calculations, because I've shown you I've shown you how to calculate, how to find this. So after finding all your after putting in all your calculations there, you find your V1. So you are going to find your V1. I don't know why it has become slow again. So after doing all your calculations, you're going to find your V1, but of course the atmospheric pressure, we know it to be, it's supposed to be something like 1.013, and then times 10 to the power 5. So times 10 to the power 5, that's the atmospheric pressure that you're going to be using. And then from there, you can put it there, you put it there, and then rho GH, gravity, you know, the density of water is known, and then you also have to include the temperatures there. T1 should be in Kelvin and T2 should also be in Kelvin. The volume has been given there. So after doing all your calculations, you find V1 to be after doing your calculation, you find V1 to be 5.198 cubic centimeters. So now this is not the volume. They are not asking us to find the volume. The question says we find the radius of the bubble. So we find the radius of the bubble just before it reaches the surface. So now to find the radius, we know to say the bubble, we're going to consider this bubble to be a sphere. So the volume of a sphere is given by 4/3 pi r cubed. So where there is V1, you just put 4/3 pi r cubed. This is equal to 5.198, and then you make r the subject. So you're going to have r is equal to the cube root of 5.198 over, so if you want, you can do this, 3/4 pi. So when you find that, you find the radius to be 1 point something, which is close to 1.07 centimeters. So this is going to be your radius. So this is the radius of the bubble that they wanted us to find. Let's quickly do the last question. Okay. So the question 4 is, in an alcohol in glass thermometer, the alcohol column has length 12.61 at 0 degrees and length 22.79 centimeters at 100 degrees Celsius. What is the temperature of the column, or what is the temperature if the column has length 18.7 and 14.6? So one thing that you need to understand is that you have a column you have, this is an alcohol in glass thermometer. So you expect the, if for instance you were to write the oasis, what we've been given in this question is just the temperature and the length. So we can say the change in temperature. So we can say the change in temperature is okay, not really equal to the change. Okay, let me just write it in terms of the ratio. That's when maybe you understand it properly. The ratio of the change in temperature and the ratio of the change in the length is equal to a constant. So okay, in short, how can I say this? Okay, we know the formula to say it's the change in L is equal to alpha L naught change in temperature. So when we divide the change in temperature, so when you divide the change in L, when we divide the change in L on both sides, you get something like 1 over alpha L naught. But remember, this is a constant because we know that alpha is a constant, which is the linear, which is the coefficient of linear expansion. This one is a constant, and then L naught will also be the constant because L naught will also be the will also be a constant because it will be the same on both for the first and the second case. So what you do is you consider this to just be K. So when you consider this to be C or K, which is just a constant, you simply just have something like this. So this will be, okay, let me just write the formulas there. So this will, the change in T is just the same as T minus T naught over L minus L naught. So from there you can now get your what's this, your values there. You plug them in to find your answers. So we know to say the temperature there was first 100 degrees. The final temperature was 100 degrees, and then the initial temperature was 0.0. This is what we've been given, and then everything divided by the final length was 22.7. I don't know if this is 9 or grams. Okay, I think this is grams. Sorry, it's 9. 22.79, then minus 12.61. So when you do the subtraction and then you divide, you get your answer to be 9.823. So this is the answer that you're going to get. This will be degrees Celsius per centimeter. That will be your units. Then from there we can use this now to find the other answers. So in other words, what we've just found here, so what we've just found is the ratio of the temperature to the length, the ratio of the temperature to the length, which is 9.823 degrees Celsius per centimeter. So this is what we found. So from there, let us now find the temperature if the column has the length 18. So how do you do that? So we say the change in temperature is given by the change, so it will be given by T1. Okay, let me just do it this way. So instead of me repeating the same thing, let me just say the change in temperature will be equal to, because we have this as our standard, to say the ratio is equal to that. So if we say the ratio is this 9.823, so if I want to find the change in temperature, it means that I'm just going to say the change in temperature is equal to 9.239 9.823 times the change in length. This is what I'm going to have. Yeah, so from there we can now say the change in temperature is equal to 9. Okay, before I even write it this way, let me just do this. Let me write the change in temperature in terms of L final and L initial. So we can say the change in temperature is just in terms of T final and T initial. So the change in temperature is just the final temperature minus the initial temperature. Then this is equal to 9.823. Then you open that, this will be L minus L initial. So this is what you're going to have. So we've been given certain values there, like the initial temperature has been given. Then what we're looking for is the final temperature. So you just make T final the subject. So you're going to have T initial and then plus, and then you have 9.2. Okay, you have 9.823. You're going to have 9.823, and then your L final is is this one here, the one that you've been given in the question. It's this one. So the L final, because they're asking us to say what is the temperature if the column has length this. So the L final, you consider it to be this one here, 18, and then the L initial you just get the normal L initial. So the L final is 18. So you open the brackets there. I don't know why it has become slow. So minus the initial that was given was 12.61. So this is the initial length that was given. So when you subtract that, the initial temperature was also given, it was 0. So here where there is T naught, you can just put 0. So we say T naught, you know that this is 0.0 according to the question, and then plus. Here when you do all your calculation, you get 59.8 degrees. So you get your 59.8 degrees Celsius. So in the first case there, the temperature that they wanted is that, and then the next temperature that they want is when is T of the length, which is 14.6 according to the question. The length is 14.6, this one here. So 14.6. So T of 14.6, if you want you can write it this way. If you want you can just say T is equal to, and then the initial temperature is also just 0 there, and then plus, of course we know that this is 9.823 open brackets. Then there we will have our 14.6, and then minus the initial temperature, which is 12.61. So this is equal to, so when you do your calculations there, you find your answer to be 19.5 degrees Celsius. So the temperature, so this was our A, then this is B. So T, when the length is 14.6 is simply just 19.5 degrees Celsius. Okay, so thank you very much for watching my tutorial videos. Make sure that you don't forget to subscribe. If you have not yet subscribed, don't forget to subscribe to the channel so that you don't miss out the other videos that I'll be posting. Alright, so these are the solutions for the first exercise. See you in the next lecture that we're going to have, or in the next tutorial that we're going to have. Thank you very much for your attention.